Isn't that wonderful? You'll become immortalized. Some people think when you take your picture, you make them immortal. I've traveled in some countries where people want you to take their picture, because they become eternal if you do that in their minds. Whether they actually become eternal or not, I'm not sure, just by having their picture taken. But they think so, and so I take lots of pictures, make them eternal. Okay, I'm gonna go back to sharing the screen again, I hope. And we're now recording. Okay, so we have a function, we have a domain D, and we have a point x naught. Because continuity is continuity of a function at a point, and you got to know the domain, because in the definition, right over here, you've got to take something in the domain. Secondly, by the way, for continuity, the point is always inside the domain. I didn't emphasize that yesterday because you had enough nonsense to look at yesterday. But for continuity, you don't take anything and talk about continuity unless the point at which you are thinking about is in the set of the domain of the function. Okay, here's the definition again written out. And what I want to stress here is what you've got in this if-then sentence. When you prove something's continuous, there's an if-then sentence you have to verify. If we go back and remember what a conditional statement is, it is true unless the if part's true and the then part's false. So the only way this if-then sentence is false is with the if part true and the then part false, okay? Therefore, we never have to worry. Somebody else is coming. I will let them in. I let in Natalie. Natalie missed a little bit, but maybe you can pick it up. Anyway, the if-then sentence, you never have to worry about the if part being false, because if it's false, the whole sentence is true anyway. So we always, when you have an if-then sentence to prove, you always get to assume the if part. You always get to say it's true. So when we do the proof of anything with this statement, we will be assuming that this is true. Okay? And what do we have to do? We have to show this is true. So it comes down to verifying this idea given this idea. Now, if you look at this statement, what do you have? You have x, x naught, delta, f of x naught, and epsilon. How many different things is that? Well, the x and the x naught, two things. Delta and epsilon, two things. And the function f. So we have 5 different things in this sentence. And what are you given? You're given the function. So if you're given the function, you ought to know what f of x is. That's the formula. And you ought to know what f of x naught is, because that's a plug-in. You put the number x naught into the formula and you see what number you get. So this little part right here is always known. This part is assumed, so it's known, except the two things that you don't know about x and f, which have nothing to do with x and f, are these two numbers, delta and epsilon. And that's what you are going to choose or be given at the beginning of a proof in this case. So the proof says for every epsilon there's a delta, so that you always, in terms of proving something, take an epsilon. Then you've got to find the delta so that when you assume this is true, you get that this is true. So the way we deal with it is to deal with the end part to see when do I make this true, given this part. And so I'm going to be stressing that over and over again until you guys get it. But yesterday, if you go back and listen to the tape, every once in a while I struggle a little bit with how to say it, because normally we talk about limits first and we define continuity in terms of limits. But you don't need to do that, as I've tried to show you. But let me try to show you something else here, namely the table of contents of the book. that we have. And I'm just trying to get the right place. I guess that's the right place. If you look at section 1, you guys are very familiar with parts 1, 2, and 3, the sections. We haven't talked about number 4. Number 4 is motivation for calculus. What are we talking about in terms of like this second chapter here is derivatives. We have continuity and we have limits that you see. With 5, 6, and 7, those are about limits. So you have limits and continuity and derivatives. That really, those concepts are what Calc 1 is all about. Okay, so what section 4 does, and we'll be talking about it, but not right now, but you could go read that. That's setting up ideas of why people study calculus and why, when calculus was invented, it became such an important thing for science. Now, so what's the book do? The book gives the definition of limit. And by the way, in section 5, he says he's going to give you the intuitive idea of what a limit is, because 2 sections later, he gives you the precise definition. So section 5 says the limit, but really section 5 says, if you read it, the intuitive limit, and section 7 says the precise limit. So the author has decided to sort of let you walk in the shallow water first, where he gives you some ideas, some pictures and stuff. The trouble is, again, we don't know what any of these things look like. We're going to verify what they all look like. So he's going to rely heavily on your past knowledge to talk about limits. And then he's going to talk about how you calculate limits. So there's some limit laws, some things to learn. And then he's going to have the precise definition. And then he's going to talk about continuity. Continuity turns out, the way he does it, as a special kind of limit. Okay? So what am I doing? I'm giving you continuity first. We haven't talked about limits yet, but when we talk about limits, it will be precise. And we'll be talking about limit laws. So I'm doing this backwards. What you're going to have at the end is you're going to have both ways to go. You'll have what I'm telling you and trying to show you. You have the author's presentation. So hopefully you will understand it, because you'll have both worlds. Now, getting back to this a second, what in the world did we do yesterday with this definition? So one more time, in terms of pictorially. Now, yesterday I drew a graph, but I shouldn't really have done that. What do you know? You know about a function, you know about an x naught, you know about a domain, and the point has to be in the domain. And you have it, since the point is in the domain, you have a value. So the point you know for continuity is you have a value and you have a height. The height is stick the number into the function, you get a number. When you put the two together, you get a point on the graph. This is what we actually know about what we're going to talk about continuity. We know where we are right there. What does all this stuff say up here? It says, in the end, again, you look at this here, this says f of x minus f of x naught is less than epsilon. That's a distance. Distance is measured on the vertical by what I hope will be big enough here, an epsilon distance. So what happens is, around the graph, we put a band. Because any x I take, like down here somewhere, the graph has to go up into this little vertical band. It's a horizontal band, but produced by vertical numbers. So I don't know anything about the graph for this. All I know is about continuity. I'm trying to tell you, we want to put all the graph ideas away, because the graph ideas, we didn't prove anything. You just believed it because the teacher in high school said it was true. Okay? Now, what you can do, of course, is use your calculator. What's the calculator do? It plots points. So all the calculator is going to do is do what I'm doing here, but it's going to take the formula and stick a bunch of x's in it. When you stick a bunch of x's in the formula and you have a graphing calculator, the calculator will produce a picture much better than this one, where you'll have a curve somehow stretched out around this area. But that's kind of missing the point. The whole idea is we're trying to build the curve. So having a machine tell you what the curve is nice in certain respects, but it doesn't tell you why we're doing it. It doesn't tell you how it works. It doesn't tell you why the machine comes up with what it is. And so I'm trying to show you the guts of the thing before we get to the nice picture. Okay. So anyway, with continuity, you stick a band around this point, around the height. Then what we got to do is find a delta so that for any x within a certain distance here. So what we have to find is an acceptable distance here. And I have no idea. If I don't know what the function is, I have no idea what that is. Find an acceptable distance here. And that's going to produce a different thing. That's going to produce a vertical band. And if we've got the right, if the function's continuous, then anytime when you get the right delta here, and the delta depends on the epsilon. If I make this band that's horizontal narrower, I might have to make the band around the x naught, the horizontal one, narrower. So the width of this band depends on the width of that band. Yesterday we found out that if we had the identity function, we could take the width of this to be the same as the width of that. Okay. On the other hand, if I had the function given by 2x plus 1, we would have to take half the distance here in order to get the graph to fit, because what has to happen between here and here, the graph, if you have a continuous function at every point, it has to stay in this band as long as we're within here. It might get outside, it might go someplace else later, but you're zeroing in. What continuity does is zeroes in and tries to explain what we mean by near. And so if I'm in this rectangle, am I near the point? I don't know. It depends on what the dimensions are. How big are these numbers? If the distance across here is in the 1/1,000,000th of an inch or something, then this is looking at this in a microscope perhaps. On the other hand, if this is 10 feet across, this is pretty big here. The whole point of this is to have this work no matter what size. And so you might have later, and I'm going to mess my picture up now, but you might have later things like this, and you might have later stuff like this. No matter what you pick, it's still got to work. And that's the power of it. The universal quantifier is very powerful because it always gives you the right answer. So now I'm going to quit this, get off this page, hopefully. And you can see me, I guess, again. I'm going to a different screen. I actually could see a Peterson there, but she may not be happy about that. And we're going to go over to some other screen, I thought. Where's my other screen? There it is. Okay. I have lots of screens to pick here. Okay. So now we're on this continuity page stuff that we talked about yesterday. Now, what I have displayed at the moment is the square root function. F of x is square root x. Okay. Now, if you look at the proof, and we'll look at it in a little bit, if you look at the proof, it's rather complicated. Now, actually, anything I can put in about 2 inches is not complicated. Okay. I've worked on some things in research where to write down the question that we're talking about takes over an hour to write it down. That's totally different than understanding it. That's just writing it down so somebody can see what we're talking about. It takes an hour to write down. That's a lot bigger than something that's this wide. So I don't consider this very complicated. However, if you don't know what you're doing, this is like hieroglyphics, and we'll be talking about it. But a little more complicated function, a little more complicated response, which we will consider in a little while. But I want to go back a little bit and go back here in case you haven't read all this yet. Here's this same definition I talked about before. And what I want to mention here is is the names of these examples. Constant function, identity function, linear function, affine function, that just means a straight line, absolute value, the squaring function, and the square root function. Now, the whole point of this is to say this definition that I gave you, whether you believe it has anything to do with continuity of a graph and unbrokenness and all, it doesn't matter. For each of these functions, if I'm clever enough, I can use the definition to verify something. Now, I claim that what it verifies is continuity, but we don't need to know that. The point is all these functions you know about all satisfy the same definition. This wild thing, all of them can be looked at and you can do this thing for all of them. It turns out that we're going to show, not today, but that the sine function also this works, the cosine function this works, exponential functions, logarithm functions, and so on. Generally, all the functions you know, polynomials, rational functions, third cube roots, whatever, all of them satisfy this idea because all of those functions are continuous. And so I just put down a few simple ones on these pages, and I did it so you'd see the progression of how it gets harder. Each one of them is meant, I put it in to say it gets harder, okay? Now, if we go beyond these definitions, these first functions, we get into not the particular function here, but functions in general. So I want to talk about that now, because what you have to do is you have to figure out how to do these for given functions you know. On the other hand, we want to get away from doing this thing because this is complicated. So what I want to do is study functions in general without studying a particular one. So look at all these functions, any function that you have ever heard of. And just if we just look at the names that I put on here, I put the names on here so when I go back and read this, I know what the thing's talking about, so I don't have to read all the stuff here. Reading stuff here sometimes bogs me down. Maybe I go to sleep, but I can read the bold print here and see what I'm trying to say. This says continuity at a point implies local boundedness. Oh, what in the world does that mean? That means, what's local mean? Local means within a neighborhood. And what's a neighborhood? Remember, that was something of the center was the point, and you had a radius, and you went at an interval on both sides. So if I had the number 2 and I had an interval of radius 1, that would be all the numbers between 1 and 3. That's what we mean by local. It means in a neighborhood, nearby, okay? And we use intervals to describe what we mean by the concept of nearby, close. You want to talk about close, you shrink the interval around the point, okay? Somebody tells you how close, you make an interval that big. Okay. The point is, if I have this continuity definition, whether you believe in it or not, if I have it, then near any place like x naught, the function will not be able to be too big or too small. In other words, it can't go off to infinity nearby. It may go off to infinity later. All polynomials, for example, when x gets big enough, get bigger and bigger and bigger, or in the negative sense, bigger and bigger and bigger. Okay, the sine function does not forever, but the tangent function does. At pi over 2, the tangent is infinite. So the tangent, we say, is unbounded in a certain region, 0 pi over 2. But it's continuous. So if we are a place where it's continuous, it's bounded in a neighborhood nearby. Now, what you learn here, because I need to know how big, the function is always smaller. The height here is always less high than 1 plus this number. Locally, not for all x's, but for some x's, this is true. And what do we do when we're doing epsilon delta arguments? We're deciding how close to get. you get close enough, this is going to be true right here. And I need that in some proofs later, which we'll get to. So anyway, continuity implies boundedness. Now, what's this about? If I have two functions for which they're both continuous somewhere, then the sum is continuous. And the proof, notice, gets longer. We're going to come back to the proof in a little bit, but right now I'm just trying to talk about the heavy print here. Sums and products of continuous functions are continuous, okay? So if you have a complicated function and you want to know whether it's continuous or not, you break it up maybe, into smaller pieces and study them. What does this one say? If I multiply a function by a constant, like twice, or 3 times, or negative 3 times, additive inverses, that has to do with putting a minus on it. So instead of f of x equal x squared, you have f of x equals minus x squared. You're supposed to know from reading section 1.3 what that means. It means it turns the graph over. We're going to talk about all that as we go. Differences of continuous functions are continuous. See, earlier we had sums. As soon as I know about additive inverses, the difference here, if I have f minus g, it always means the definition is add minus g. That's what it means. Adding or subtracting is always adding an inverse. We'll talk more about that later. Now, if I have a function and it's not 0 somewhere, if the f of x naught, in this case g, if g is x naught is not 0, okay, then locally you're going to have some values that are not 0. Now, let me stop the share here, go back to the other screen, hopefully, and show you something else here. Go back to my, didn't do it yet. Okay. This picture, and shove it up a little bit. What I'm hoping you're going to see, and this time I'm going to draw a graph, okay? So now, suppose my point x naught is here. What that, we're going to go back to that writing in a second, but what this basically says is if f of x naught is not 0, then nearby the function cannot be 0. In other words, it's going to take a while for it to become 0. It can't just right immediately become 0. Now, the point is that any other place, it's going to take a while for it to get, it might be like this, but it can't just become 0. If it became 0 right away, for example, then, and never was what I just said here, then it's jumping, and that's not going to be continuous. So the point is, it can't get from here down to here without passing through 0. And we're going to learn in this section 7 that that's called the intermediate value theorem. In high school classes, sometimes you search for where the function became 0. It was called a root or a 0. And all this thing I just tried to point out to you in those notes is that if you have a function that's continuous and the value is not 0, it cannot just jump over 0. It has to get down there. And so it has to have a picture like this. Maybe, I mean, you know, the thing might look this way. I don't care how it looks, but the point is it can't just jump down across 0. That's what the other screen says. I'm going to go back to it, hopefully. The other screen says that if I have a continuous function which is not 0 at x naught, then there is a delta, that's a distance. So if I'm saying that delta, then the function value is bigger than half. And we're going to use that. That's called bounded away from 0. Okay, why do I need that? Because I might be talking about reciprocals. Reciprocals of functions means turn them over, 1 over. So I need to talk about if I know a function is continuous, what about turning it upside down? That's another thing we did in section 1.3 review, if you remember. So it's nice to know if a function is continuous, and then instead of that, you have this function that's also continuous. Okay, and there's a proof. We'll get to the proofs. Quotients of continuous functions. Once I know reciprocals are continuous and products are continuous, I can write a product f over g as f times 1 over G. And if I know products are continuous and I know 1 over G is continuous, I know, see how short this little proof is? By the previous theorem, this is function's continuous. And so I can write this as a product. As soon as I write it as a product, the product's continuous. So this is real short. This is the power of using theorems to prove theorems instead of epsilons and deltas. And we come finally to the last one here. The composition of continuous functions is continuous. And now this is going to take a little more trouble. Another thing you can do is take the maximum and minimums and stuff, but you may remember yesterday I told you all we're going to talk about in this class right now are the first 6 pages. So right now you don't have to pay any attention to stuff on page 7 except for this little extra part from page 6 because this proposition spilled over a little bit. So what I want you to do is basically stop right here where these asterisks are and not worry about any of this stuff down here unless you want to. Nothing wrong with it. It's nice, good math, but we're not going to have to worry about it right now in our class. So basically, what does page 6 and 5 and so on and back down here, what do all these things say? They say arithmetic of continuous functions produces continuous functions. Okay, so if we know we have a complicated function and we can break it up into sums, differences, products, reciprocals, compositions, and we know the parts are continuous functions, then those more complicated things are continuous. Okay, so that's what the notes are about. Now, okay, yesterday, and so I'm gonna stop the share right now and go back to my other share, which is the screen. And hopefully in time I can get good at doing that quickly. And I'm going to go here and turn a page over. This is like erasing the blackboard and talk about something else. Okay, so what have we been talking about? Continuity. And we talk about continuity at a point, but if I have continuity at every point, that's what's going to produce the graphs that you have seen, which are unbroken. But we're going to have to get to that, okay? Okay, but suppose I have a graph and I know it is broken, okay? So from a mathematical standpoint, the interesting place is where it's broken. Now, if I don't pay any attention to half of it, then what I've got is looking at the end point of a graph, so to speak. That's what it looks like. Now, our definition that I've given you works for endpoints as well as interior points. One of the differences when you read sections 4, 5, 6, or 5, 6, 7 in the book, the author is always talking about interior points of an interval, so that there are points on both sides of a given point x naught that are in the domain. But for this thing, if I stopped at x naught, that's what we call the endpoint. In the book, but the way the author does it, when you do it more shallow than we're going to do it, you have to make a special case for endpoints. So the author is going to have 3 definitions. In my way of doing it, it's 1 definition, because our definition is going to cover endpoints. His definition does not, because his definition is only going to talk about interior points. So when he does it, he's going to do endpoints, but he's got to assume some new definition for that. And the other thing that we're going to do one of these moments is continue the graph to plus or minus infinity. Like if you think about, if you know the graph of the sine function from trigonometry, it goes up and down and up and down and up and down, and it keeps doing that forever. So it's what's called a bounded function, but it keeps oscillating up and down, up and down, and up and down, and so on. But the x's can go to infinity. we need to talk about limits at infinity as well. So again, with my definition, we'll have accumulation points. It's all one definition. With the author, he has to have two more definitions. So he's going to have 5. And I'm going to show you the difference when we get there. Anyway, right now, though, we could talk about continuity at any point along here. And if I go the other way, we could talk about continuity of the other part of the graph here. The problem is we haven't yet addressed what happens here. Now, you have to trust me for the moment just with my picture, because I don't want to draw any graphs right now. But you have to kind of trust me that what we've been taking care of are the two pieces up to now with continuity. The trouble is continuity does not take into account this new point. So let's look at it a little bit. If my domain, in my picture here, my domain extends from here out to about here. This is my domain. That's where the function is defined. Okay? Evidently. Now, I don't know if it's defined at x naught or not. But I can approach x naught from the left-hand side, or I can approach from the right-hand side. If I approach from the right-hand side, and I believe in this curve, then the limit, the continuity, I will bring up limits in a minute, the continuity has to do with what's happening to these points. As I get closer and closer to x naught, the function values are getting closer and closer to a certain height. Okay. On the other hand, if I'm over here and I get closer and closer to this point, the function values are getting closer and closer to some number like here. So if the x naught is in the domain, I have to have a point for it, right? F of x naught, I have to have one. Where is f of x naught? Well, it could be way down here. Or it could be up here. It could be just right there. It could be in the middle. It could be just exactly there, or it could be up here. Okay? But we're going to find out that there's no way to make the function continuous at that point. Why not?
Because it's separated.
Well, it is, but let's go to epsilons and deltas. If you tell me that you think, suppose this is f of x naught, suppose that's f of x naught down there, okay? What do we do with continuity? You take any epsilon, any number around here, remember? We have to find a number around x naught so that the graph is in here. Where's the graph? The graph, unfortunately, for this point, is way up here. So this, if the function is defined to be this number, there can't be continuity because you can't get the graph into this box. Now you can change the size of the box all you want, but you're never going to make a box that's going to have the graph in it. So if the function value is down here, it's certainly not a continuous point. But now, what if we put the box up here? And my picture is going to get messed up. But I can put a box around here that doesn't get the graph either. Right? What if I put a box right around it? Suppose my function value happens to be right there. Then my box is going to include part of the graph, but the other part's not in there. And what did the definition say? I have to turn my page over, but it said for every epsilon delta such that for anything in the domain, if it's close enough, well, there are things on the right-hand side here that are as close as you please to x naught, but the graph's way up there. So the point is that maybe you don't believe what continuity gives you, but I think you can easily see what continuity does not give you. If I have a break in the curve, you can't have continuity there. So you might have to think about that a little bit. Now, but I might be able to talk about what happens from the left. And so if the point joins this curve, we're going to say it's continuous from the left. If on the other hand, the point happened to be up here, right at that spot, that would be continuous from the right. But this particular graph exhibits what we call a jump discontinuity. Now, if you were on a road traveling along here and you cross this point, you're going to make a jump. And if you didn't know the jump is coming, you're going to be also surprised. All right. We can also have what are called infinite jumps. I can have a graph that on one side looks like this and on the other side looks like this. That's an infinite jump across that vertical line. So we're going to be talking about discontinuity as well as continuity. But in order to do that, we need to bring in a new idea. Because one, I don't even know if X naught's in the domain. We only talk about continuity if it's in the domain, but I can have these two graphs, these two pictures, without any point in the middle.
So if there's no point in the middle, would it be like an open circle or?
Well, we need to bring it, what we need to do, you need to ask your question in a few more minutes, okay? Because what we need to do is to bring in the concept of limit.
Okay. So I mean, I'm trying to understand this, but basically what you're saying is from that point in between those lines is continuous.
Yeah, let's make a new picture because that one's kind of screwed up. Okay. So really what I have, if I make the same idea here, I got this kind of a picture, okay, on both sides. And what I mean for this to do is to go right up here, hopefully, when I drew my picture, whether or not, see, if the point is not, no, okay, here, we know what the domain is, at least part. We know the domain goes from here to here and here to here. We don't know whether X naught's in the domain or not. It could be open intervals here.
Okay, so that's what you're trying to get across. So this could be a closed bracket or an open bracket.
And so we might, yeah, you might have, you know, maybe, I mean, what we have here in life when we're driving is you might have had a bridge out and you can't get from one side to the other, or you might have had an earthquake and the road is at different heights at one spot because of the break in the road and you can't cross there. All right, so the point which used to be part of the graph is no longer part of the graph because of earthquake or something. Okay, if you're in Hawaii, maybe you have lava going across the road, which is something you don't want to try to drive through. Some of you drive through water, but don't drive through a magma from a volcano. You wouldn't want to do that unless you had your mother-in-law or something in the car. I don't know. Anyway, so we need to have a new concept here. And I want to do continuity first to get one thing across, but I also want to talk now what happens in a situation where, first of all, I may not have the point in the domain. And let me do one more thing. Suppose the graph looks like this. So that here's my X naught. And again, suppose I've only got the function defined and it's not defined here. Suppose this is 1, this is 2 and 3. And so suppose my domain of my function is 1, 2, union with 2, 3, but does not include 2. Then in this picture, I got a hole in the graph. Okay.
So when you connect that by a circle, an open dot, I guess, and then.
Well, the domain is open set. The graph maybe looks like this, but there's a hole in it because it's not defined at that point. Every time you define something, a function or point, you get a dot. And the dot's missing here because it's not defined there. So we can't talk about continuity here because the point's not in the domain. Okay? For continuity, the point has to be in the domain. And that's because, if I turn the page over here, you have to take f of x naught right here. You can't take f of x naught if x naught is not in the domain. So for continuity, f of x naught's in the domain. If we want to generalize continuity, that's going to be what we call limits. And that's going to take care of situations like this, where we have a hole. It's going to take care of situations like this, where we have a jump. It's going to take care of situations like this, and more general ones that I haven't pictured yet. So what I want to go to now is a new definition. And so now we're going to have a function. We're going to have a domain like I started with at the beginning of class today. I don't know how well you can see that D. And I have an x naught again. But now I'm going to have a new thing called L. And L is going to be called the limit. It's going to be a number. So this new thing that did not exist for continuity, and when I say it didn't exist, it actually does, but it's f of x naught. For continuity, I can calculate it because I know f and I know x naught. But now I'm going to be talking about something where I don't know whether x naught is something I can take f of, because x naught may no longer be in the domain. Well, if I can't take f of x naught, I can't use that other definition. Okay, so I have to introduce a new point here. And now, what's the definition? It is for every epsilon, there's a delta, such that for all things in the domain, you might say, hey, this looks pretty similar to what I had before. I think maybe I can move it and make it appear better. If, now, this is going to be a little slightly different, but what I'm writing so far is not. This is undone yet. I have something else to do here. Then f of x minus L is less than epsilon. Now, there's something else I have to add, and that is right here. So I'm underlining the two things that make this different. So I know it's having trouble zeroing in. See if I can fix it with my fingers or something. Come on, machine. Okay. So if you got to know the other definition, then except for the two things I underlined here, it's the same. Now, what's the left one here? What is this thing here? Why did I put this in here? Because for limits, we don't want the x to be equal to x naught. We don't want to be at the point because the function may not be defined at the point. So we have to take something besides x naught that's close. That's what the x minus x naught less than delta tells you it's close. And what's different is this L. It's called the limit. Now, if the function's continuous, we know what the L is. It's f of x naught. But if the function's not continuous, we're going to have to figure out what the L is before we do any limit work. And it's 20 after. I have one more thing to say. We have a notation to develop. And the first thing I'm going to write is too much and too little. For those of you who have had calculus before, what I'm writing now will not be what you had before. This says, I want to talk about the limit of the function at the point x naught, and I want to say that equals a number L. All I need to know is, what do you think the limit is? Where are you talking about? And what's the function? That's all that's required. What have you seen before for those of you who have done some limits before?
Usually it had x2 and x, then an arrow to infinity, some other number.
And you see this, and you see this. Yes. This is what you're used to seeing. Now, this is a good notation and a bad notation both, because we don't, with limits, we really aren't moving. The x never moves. The x is close, but it's not changing I mean, well, sorry, it is changing, but you're picking something close enough. So the arrow is a little bit, it's like it's moving toward it. Now we do that because sometimes with time, we do think about time moving forward or moving backwards and stuff. Anyway, we're over our 20 minutes here in terms of being over time. This is what you're usually going to see. And it's mainly because we usually see a function by its formula instead of its name. Okay? So this is this. And so in this context, and then I'll quit, what is continuity? In this context, we can write this like this. So one is what is a limit, and the other is what is continuity. All continuity does is tells you what the limit is. If the function's not continuous there, we don't know that, and therefore we have to find the limit. So this limit's harder. This is one of the reasons I wanted to do it first.